condition. What about when L is not equal to 0 and still when R is very close to the nucleus? Okay, so what happens to our Schrödinger equation then? Well, once again, when R is very close to the nucleus, right, we eliminate that whole side of the equation because U of R will be a very, very small function. All right. But now also the electron has orbital angular momentum and it's being flung away from the proton, right? So if you think about that, right, imagine you're in the famous carnival ride or fair ride, where you sit and you lean up against that wall and it starts spinning you around and they drop the floor out, right? But you stay in position because your angular momentum is flinging you outward. It's flinging you like right up against that wall and you're thrown back against the wall and they can drop the floor out and you won't fall down, okay? So this same thing is happening to the electron. The electron's whizzing around the proton at great speed and thus it has a large enough angular momentum that attractive force is no longer important. So when R is equal to 0, its angular momentum is strong enough to dominate the attractive forces, and thus the electron is being repelled from the nucleus. And now specifically, the reason why we can ignore our Coulomb potential, right? So I'm going to cross that out because you can see in my approximate Schrödinger equation that Coulomb potential is no longer there. Well, this gets into what I like to think of as the quantized ice skater, right? So imagine you're spinning around and around, right? Your hands are spread out. What happens when you bring your center of mass closer in? You spin faster, right? You go much faster when you bring in that center of mass. The same thing is going on with this electron-proton system. The closer that electron is to the proton, the larger its angular momentum is, and the more it's getting flung out. So to me, this is the really cool age-old wisdom. If you ever have paused to ask the question, if the most likely place of finding the electron is near the nucleus, why isn't it right at the nucleus? And the reason for that is because it has angular momentum, okay? Because it's being attracted to the nucleus, but it's also being flung away from the nucleus at the same time, okay? So in this case, when R is very, very close, we can ignore the effective potential term. And when I push through all of my constants, I get this very simple Schrödinger equation to solve for the radial wave function. And the approximate solution is just simply A times R raised to the L power, where that's the same L quantum number. Okay, that's the quantum number L. Okay? And so again, like I said, all of these are approximate solutions because what we're going to have to do is combine all of these into one solution eventually. All right? So let's look at the last condition. Oh, and sorry, the last thing I want to compare is, so the reason why, though, if you want to think about Coulomb's law and angular momentum being in competition, Coulomb, so the force, that's what that F is for, the force of Coulomb's law is proportional to 1 over R. However, the force of angular momentum is proportional to 1 over R squared. Right, there it is. There's the R squared, and there's the R. So for a very small r, when you take 1 over a very small number and then square it, that gives you a huge force due to angular momentum, much larger than the force due to Coulomb's law. Okay, so hopefully that makes good sense.